welcome to another tutorial on the use of ArcGIS and understanding GIS data. So today we'll be looking at how we can be able to convert our file, our data, from a geographic coordinate system to a projected coordinate system. Now, one will ask, why do I need to convert my data? First of all, you need to understand that geographic coordinate system is like getting the data of Earth on a globe, which is the longitude and latitude, degree, minutes, and seconds, decimal degree and minutes, or geographic coordinate in the sphere. That is coordinate on a sphere. So when we talk about projected coordinate system, we are talking about projecting what we now have on that round Earth on a plane surface so that we can be able to get measurements. So if you are looking to use your data for measurement analysis that has to do with distance, matrix, or meter distance or kilometer, then you need to convert your data from a geographic coordinate system, which is GCS, to a projected coordinate system. So the two data I'm going to be working with is I'm going to be working with a vector data, which is a boundary data, LGA boundary of my study area, and you are going to be also working with DEM. So DEM is a raster-based image. So what we are looking at, how do we convert a vector data, and also how do we convert a raster data? Note, it's very important to understand the process. And for instance, for you to be able to understand the conversion, you need to know or determine the exact coordinate system which is in projection of your area or your study area. I'm going to attach a file below this video where you can be able to download a grid, a word grid, to be able to determine which projection or which location your data or your location falls within. So for us to be able to achieve this, we are going to be using our ArcToolbox. ArcToolbox is a toolbox in GIS, which we can be able to use to get our various data management and analysis tool within the GIS environment. Okay, so for us to be able to achieve this, we are going to be using our data management tool, which is this is your data management tool. So that's what we are going to be using. So in your data management tool, we are going to go down to projection and transformation. So you open up projection and transformation. So for raster data, you are going to be using raster, which is under the projection and transformation tool. For vector data, you are going to just be going to these tools under the raster field, which is project. So for raster data, which we are starting off with, you are going to click and expand the raster data file, and then you are going to click on project raster. So you are going to double click on it so you can open the dialog box. So I'm double clicking on the project raster. So now the project raster is open. So first of all, you're going to add your raster. So we're going to add our DEM, data, raster data inside our GIS environment. So now you can see that from the raster information, the input data coordinate system is a GCS WGS 1984. So GCS stands for Geographic Coordinate System, while WGS stands for World Geodetic System of 1984, which is what we popularly use. So now you are going to select your output raster data set. So I'm going to open up the output area, and I'm going to locate my file folder where I'm going to be saving my file. So for this particular folder, I'm working with Nsoka LGL land use, which is my folder. So I'm going to open up the folder and I'm going to save it as DEM underscore BROJ. You can decide to leave out the underscore, but you need to understand that how database function, it doesn't accept spacing. Is either use underscore or you write your letters together. So, but I want to have a variation between the two. So I'm using DEM underscore PROJ, which is projection. So I'm going to add the TIF extension to it so that it will be on a TIF format, the way I normally prefer my file. So I'm going to click on save. Then for the output coordinate system, this is where you are going to work. So for instance, the area which I'm studying falls within the UTM, which is a type of projected coordinate system, and it is 32 knots. So the UTM stands for Universal Transverse Mercator under projected coordinate system. So I'm going to be setting it to this projected coordinate system of my area. So I'm clicking on here and I'm going to go to projected coordinate system, and I'll open it up. Then I'll go down to UTM and I'll open up UTM. Then I have to go down to WGS 1984, which is the one we are going to be using. So I open up, and my area, because it's 32 knots or 32 N, is falls within the northern hemisphere. So I'm going to open up the northern hemisphere. So I'm going to scroll down to find 32 knots, which is here. So this WGS 1984 UTM zone 32 knots, which is the zone where my study area falls. And I'm going to click on OK. Just like I said earlier, if you don't know your zone, you can be able to browse about that or use the file which I'm going to attach under, which has a download link to download the world grid to see where your location falls. Okay. So now the next thing I'm going to do is I'm going to click on OK. So if I click on OK, the system is going to analyze my file and convert them into a projected coordinate system from a geographic coordinate system. So you can see the system is done. We now have a projected coordinate system right on our screen. So if I go back to my table of contents and I open up the old file and I click on properties, we are going to go to source, and from our source you can see that this file is a GCS WGS 1984, which is a geographic coordinate system. Now if you go to our new file and open it up, properties, source, and we'll scroll down, we are going to see that our new file is in WGS 1984 UTM zone 32 knots, and the linear unit is meter. Okay, so if I go back to the previous file, you can see that the linear unit is missing. You understand? So that is it. So also for us to now convert our vector file, which is a shape file, we are going to go back again to Arc Toolbox, and instead of using raster, we use project, which we are trying to project what we have in geographic coordinate system into a projected coordinate system. So we are going to double click and open up project, and then we are going to add our data set, which is LGA boundary. So you can see that the boundary is in GCS WGS 1984, which is a geographic coordinate system. Now, what is the output data set? We are going to set the output and use it as LGA boundary projected, PROJ. So why do we use projected? So that we can be able to differentiate between the normal one, which is in geographic coordinate system, and the current one, which is in projected coordinate system. Then we click on save. Then it's going to ask us for our output coordinate system. You do the same, repeat the same process here. You go to projected coordinate system and open it up. Then you scroll down to UTM and open up UTM. Then you scroll down to WGS 1984 and open it up. Then we are looking at northern hemisphere, which is our area. We select northern hemisphere, and we're going to scroll down all the way to 32 knots, which is the zone for our data or our location, data location. Or press OK. And once we do it, we are going to press OK. So we press OK and wait for the system. So the system is done. We have projected our data. If I go back to our table of contents, it doesn't appear here, but also I can be able to add them up. So if I go to my file, I go to add data, I select add data, I can locate my data, which is LGA boundary projected.shapefile. So I'm going to click on add, and the system is going to add it. So you see our new file now, which is in projected coordinate system. If I right click here and I click on properties and I go to source, you can see that our coordinate is in projected coordinate system and projection is transverse Mercator, right? If I go to the previous file, right click and click on properties and then to source, you can see that it's geographic coordinate system. So now let me give you an insight of what projected coordinate system does using a shapefile. So if I'm trying to calculate the area of this particular boundary, right? I right click on my layer and I click on open properties. If I click on here and add my field, let me call it area, and I'm going to make it a double, because double is a real number which allows you to have decimals, and we are sure that this area is going to have decimal. That is why we are using double. So double is like a longer decimal and bigger value, while float is a shorter number but decimal. So we have short integer, which is whole number, short whole number that is not very long, while long integer is a long or large whole number. So we click on double and OK. So if I right click here on top of the area and I click on calculate geometry, the system is going to ask me, you're about to calculate a geometry. I say yes. So it's going to ask me, you see, coordinate system. So unit, you are seeing that the unit here is decimal degree. There's nothing else you can see here. So it's going to give me the value in a decimal degree, which is 7.35334, which we are sure that is not the area of this study, right? But if I go back to my LGA boundary, open attribute, and I add the same thing, I do the same thing, adding area, then making them double, and OK. If I right click here and say calculate geometry, yes, you see that I'm having unit square meter. The coordinate system is PCS, which is projected coordinate system, and our unit is meter. So you can decide to make it meter, kilometer, acre, area, acres, hectares, and all that. So let's say we want to have it in meter, square meter, right? We press OK, and yes, and you can see that our area is in square meter, and this looks more, and is the actual size of this environment, while the other one does not portray the same thing. So if you go again side by side, you can see area is in 7.35334, which is not accurate, while the projected coordinate system is having 49726296293.126 meters, square meters. So that is it. So thank you for your attention, and if you like this kind of video, don't forget to follow, like, and share. Follow us and subscribe to our YouTube channel so that we can keep making wonderful and educative videos like this. Thank you very much.